Hey everyone, and welcome back for another deep dive. Today, we're tackling something that's been a real head scratcher for, well, centuries really, the three-body problem.
Yeah, this was a classic.
We've got some great material lined up, excerpts from a physics textbook, a few scientific articles, and the goal is to, well, first of all, figure out what this problem even is.
Right, because it's kind of deceptively simple when you first hear it,
Exactly. Then we got to get into why it's so notoriously hard to solve.
which is, believe me, harder than it sounds.
And then why people have been so fascinated by it for so long.
Because there's a reason it keeps coming up, even centuries later.
So to kick things off,
Yeah.
what is the three-body problem? Like, imagine I don't know, someone who's heard the name that has no clue what it means.
Okay, so picture this. You've got three objects out in space, could be stars, planets, whatever.
Like spaceships, even?
Sure, spaceships, anything with mass, really.
Mhm.
The point is they're all pulling on each other with gravity.
Right, good old gravity.
The question is, how do you predict where they'll all go? How do you figure out their movements over time?
Which you'd think wouldn't be that hard, right? We can do it for the Earth going around the sun, no problem.
Yeah, that's the two-body problem. Newton figured that out ages ago. We've got nice, neat equations for that.
So just add one more thing in there and boom, we're done.
If only it were that simple. See, that third body throws everything out of whack. Suddenly those neat equations don't cut it anymore.
So we can't just, like, plug in the numbers and get an answer.
Nope. The three-body problem doesn't have what we call a closed-form solution. There's no single formula that magically tells you where everything will be at any given time.
Okay, so even with all our fancy math, we hit a wall.
Pretty much.
Yeah.
It gets really complex, really fast.
Huh. So to make sure I get this, it's not just that the math is hard, it's that the system itself is, like, inherently unpredictable.
You got it.
Well,
It's kind of like, imagine you're trying to predict where three billiard balls will go after your break.
okay, I can kind of picture that.
But now imagine those balls have invisible forces pulling on them the whole time, changing their paths. It's a chaotic system.
Chaotic. Okay, now we're getting into some serious science-y terms here.
Well, it's a classic example of chaos theory. The idea is that even tiny changes in the starting conditions can lead to huge differences in the outcome.
Oh, I've heard that before, like the butterfly flapping its wings causing a hurricane thing.
Exactly. It's a bit of an exaggeration, but it gets the point across. In the three-body problem, even a tiny measurement error can throw your predictions way off.
So basically, it's a cosmic guessing game.
In a way, yeah. And this isn't a new problem either. This has been stumping people for centuries.
Speaking of which, didn't Newton himself wrestle with this, like way back in the day?
You bet he did. 1600s, Isaac Newton, the father of gravity himself, was trying to figure out the whole Earth-Moon-Sun dance.
Which, I mean, if Newton couldn't solve it,
It tells you something, right?
yeah. But I thought I read that even before Newton, people were kind of bumping up against this problem.
Oh, absolutely. Amerigo Vespucci, back in the 1500s, he was using the moon's position for navigation.
So it had real-world uses even then.
Totally. And Galileo, with his observations of Jupiter and its moons, they were all touching on aspects of the three-body problem, even if they didn't have the math to fully describe it.
So this wasn't just some theoretical brain teaser. Okay, that's pretty cool. But I gotta ask, what does the math behind this problem look like? Like, without getting too deep in the weeds, can you give us a peek?
Sure. Basically, what we're trying to do is describe how those gravitational forces between the three bodies affect their motion. We're talking forces, acceleration, how their positions change over time.
So it's kind of like choreographing a dance, but the dancers keep changing their steps depending on what their partners are doing.
That's a great analogy. And that's exactly what makes it so hard. There are different ways to write the equations. You've got Newtonian mechanics, Hamiltonian mechanics.
It's different styles of dance.
In a way.
Yeah.
But no matter how you slice it, the challenge is the same.
Mhm.
Solving those equations in a way that gives us reliable predictions.
Okay, so we've established this thing is old, it's hard, and the math is pretty intense. But does that mean it's completely unsolvable? Have mathematicians just thrown their hands up in defeat?
Not quite. There are actually some special cases where we can get nice, neat solutions. We'll get into those next time.
Oh, so there are times when those three billiard balls actually behave themselves? I can't wait to hear about it.
You and me both. Well, we got to fast forward a bit to the early 1900s. There's this Finnish mathematician, Carl Sundman, and he actually comes up with a general solution for the three-body problem.
Hold on, he actually solved it. Like, after all those years, all those brilliant minds hitting a wall, he cracked the code.
It was a huge deal, but there's a bit of a catch. His solution, it's what we call an infinite series.
Okay, infinite series.
Basically, it involved an infinite number of calculations. Theoretically, it works, but in practice,
Mm-hmm.
it's just way too computationally intense. Like, it would take forever to actually use it for real predictions.
So it's like you have the map, but it's so detailed that it takes longer to read the map than to actually just walk the path.
Exactly. Brilliant solution. Theoretically, practically, not so much.
Okay, so back to square one, kinda. But I'm guessing the arrival of computers must have shaken things up, right? Even if we can't get that perfect equation, we can at least brute force it with computers, yeah.
You're absolutely right. Computers have been a game changer. We might not have that elegant solution, but we can simulate the three-body problem with incredible accuracy.
So instead of solving the equations directly, we're like making a super detailed movie of what those three bodies are doing.
That's a great way to think about it. It's called numerical integration. Basically, you break down the problem into tiny time steps and let the computer crunch the numbers for each step.
Okay, so we're not getting a perfect answer, but we're getting a pretty darn good approximation.
And the cool thing is, these simulations have revealed some really unexpected behaviors, like stuff we never would have predicted just by looking at the equations.
Wait, there's more weirdness in this problem. I thought we covered all the bases already.
Oh, there's always more. For instance, did you know there are solutions where the three bodies can move in stable figure-8 patterns?
A figure eight. Seriously, like they're just chasing each other through space forever.
It's a cosmic ballet. And that's just one example. There are tons of other complex, beautiful choreographies that we're still uncovering.
So somewhere out there, there might be stars actually doing this figure eight dance.
Yeah.
Wow, it's kind of mind-blowing.
It really makes you appreciate the complexity of the universe, right? And the cool thing is, we're not just using brute force with computers, we're also using machine learning to analyze all the data from those simulations.
Okay, so we're giving the computer a crash course in cosmic choreography and seeing what it comes up with.
Exactly. It's helping us spot patterns, maybe even find new types of solutions we haven't even thought of.
That's awesome. But even with all this, I'm still curious, are we any closer to finding that elusive general solution? The one Newton himself couldn't crack.
That's the million-dollar question. And honestly, I don't know. But the progress we've made, especially with computers and machine learning, it gives me hope. Maybe, just maybe, we'll get there someday.
Well, I'm rooting for team science on this one. But you mentioned something earlier, the restricted three-body problem. Is that like a diet version of the main problem?
Huh, sort of. It's still a three-body problem, but we make one assumption. One of the masses is way smaller than the other two.
Okay, so like a tiny asteroid caught between two giant planets.
Exactly. And even though it's simpler, it still has tons of real-world applications, like understanding satellite orbits, spacecraft trajectories,
Yeah.
that kind of stuff.
So we're really using this knowledge to like design missions and explore space.
Absolutely. It helps us figure out how to send probes to other planets, navigate through complex gravity fields. It's pretty amazing how this seemingly abstract math problem has such a big impact on real-world exploration.
I'm starting to see how this three-body problem, in all its forms, is like this fundamental key to understanding how things move in the universe. It's not just a brain teaser. It's like baked into how the cosmos works.
That's a great way to put it. And what's really fascinating is that this problem, even after centuries of study, still has so much to teach us. It's a constant reminder that science is a journey, not a destination.
And sometimes the most interesting discoveries come when we least expect them. Speaking of which, I think we got to wrap up this part of our deep dive here. But don't worry, we'll be back soon with even more insights from the world of the three-body problem.
Well, there's a good point there. It's tempting to think chaos just means everything's random, but it's not quite like that.
So there's actually some method to the madness.
Yeah, in a way. See, even in the three-body problem, even with all the unpredictability, there are still structures, patterns that emerge.
Like what kind of patterns?
Well, think of it like different types of dances. You've got your waltzes, your tangos, your hip-hop. Each one's got its own set of moves, its own rhythm, right?
Right, okay, I'm following.
Researchers have found something similar in the three-body problem. They've discovered what they call families of solutions.
Families, like orbits that are related to each other.
Exactly. Orbits that share certain characteristics, certain patterns. It's like the universe has its own repertoire of cosmic dances, all governed by the laws of physics.
Okay, that's a pretty cool way to think about it. So even in the chaos, there's a sense of order, like a hidden language we're trying to decipher.
That's a great analogy. And that's really one of the big challenges for researchers figuring out what that language is, what those underlying principles are that create these patterns.
So it's kind of like we've been handed the sheet music, but we don't know how to read it yet. We see the notes, but we're still trying to figure out the melody, the whole composition.
You got it. And with all the advancements we've made, computers, machine learning, all that, it's like we're getting closer and closer to finally understanding the music.
Okay, so maybe that ultimate general solution, the one that's been eluding us for so long, maybe it's not so far-fetched after all.
I'd like to think so. These new discoveries, the tools we're developing, they're giving us a whole new perspective on the problem.
So the journey continues. But you know what? Beyond all the math, all the technical stuff, the three-body problem really makes you step back and think about our place in the universe, you know?
What do you mean?
Well, it kind of throws a wrench into the idea that everything's predictable, everything's predetermined. If something as seemingly simple as three bodies can be this chaotic, what does that say about the bigger picture?
That's a really interesting point. It kind of challenges the whole notion of determinism, right?
Yeah. Like, even with all our knowledge, all our fancy tools, there are still limits to what we can know, what we can predict. And honestly, part of me finds that kind of unsettling.
I get that. But I also think there's something kind of exciting about it, you know? It means there's always room for surprise, for the universe to throw us a curveball and show us something new.
Yeah, I guess you're right. It's a reminder that science is all about exploration, about embracing the unknown.
Exactly.
Yeah.
And who knows, maybe someone listening to this right now will be the one to make the next big breakthrough in the three-body problem.
That's a great thought. Well, I think it's about time we wrap up this deep dive. We've covered a lot of ground today, the math, the history, the philosophy. It's been quite a ride.
I've really enjoyed it. It's always fascinating to explore these big questions with you and with our listeners.
So, to everyone out there listening,
Mhm.
we'll leave you with this. What other examples can you think of where something seemingly simple turns out to be incredibly complex? Maybe it's something in your own life, maybe it's something you've observed in the world around you. And how does that change your perspective? How does it make you think differently about things?
Yeah, keep those questions in mind. Because the three-body problem teaches us that the universe is full of surprises, and it's often in those unexpected moments that we make the most amazing discoveries.
So keep exploring, keep asking questions, and keep diving deep. Until next time.